it's listening in. Right. And you can start whenever you want.
I'll go like 6:30.
Is it streaming?
Sure, you can check it out.
Yeah, I'll check it out. Is Kashagra here?
No, he's not.
No.
I don't think so.
Tell him to do the announcement for the live stream.
Announcement where?
Discord?
I see it. It's working. I hear the audio too.
It's just e-board meeting today, right?
Yeah.
Okay, fine.
All right, we can get started. This is ML Mondays lecture 5, and make sure everyone signs in. If you guys do that, just give a thumbs up. I can get started. All right, everyone's good? Okay. All right. Today we're covering feed-forward neural networks, and again, this is the introductions for the groups. I'm Sherniket Subramanian. I'm one of the ML lecturers, part of a team with Alvin. If you can say hi. Karthik, say hi. And then Siobhan is here too. So, last week we took a pretty big conceptual leap. We explored how models actually learn through optimization, gradient descent, loss functions. We saw how models start with randomly guessing and how wrong they are, and they slowly adjust their weights to try to get better. That was the process of learning. Today we'll be focusing on the structure of those models. Pretty much what's inside of them, what does a neuron mean, for example, in machine learning, and how does data move through a network? How do layers interact to produce meaningful outputs? Hopefully by the end of the session, you'll be able to look at a neural network and understand everything from input to output. Quick recap again from last week. Remember that machine learning is essentially optimization. The model starts off clueless, makes predictions, and we measure how wrong it is using loss functions. The goal is to tweak the model's parameters, its weights, make sure that the loss gets smaller over time. We used gradient descent last week, which is our optimization workhorse to do this. Think of it like hiking down a very foggy mountain and you're blindfolded. You can't see the bottom, but you take small steps in that direction, but you know when you're blindfolded, you're going down the mountain, not up. That's pretty much what it is. You keep repeating it until you reach the lowest point, or in our case, the minimum loss. We also learned about learning rate, which controls how big the steps are. So if A, for example, is too large, you might jump right over the valley and never settle down. If it's too small, you'll pretty much just walk for eternity. Finding the balance is what you want to do. And finally, we talked about feature scaling, which was pretty much ensuring just all features are on a similar scale to prevent zigzagging. That's what we call it. All right. So, why neural networks? Why do we even need it in the first place? Because pretty much real-world data is rarely ever neat or linear. Think about faces, detecting spam, predicting stock prices. None of them are actually linear. None of these relationships can be determined through a straight line, for example. Traditional models like linear regressions, logistic regressions are like you're trying to draw a straight line through a tangled ball of yarn. They'll never figure out the pattern. Neural networks solve that problem by stacking multiple nonlinear transformations. Each layer learns to represent the data in slightly more abstract form. The first layer learns the edges, the second layer learns the shapes, the third maybe combines the shapes into objects, and by the end, the network has enough of an understanding to build up. Let me ask you guys a question. If I give you points shaped like a spiral, do you guys think a straight line could separate them perfectly? Yeah, exactly. That's why you need neural networks to bend and twist the data to fit it. All right. So neural networks are pretty much loosely inspired by our brains, but we use math in this case instead of biology. In our brains, every neuron receives a signal from others. It sums them up and decides whether to fire it. In machine learning, our neurons pretty much do the exact same thing, but mathematically. We just take weighted inputs, add a bias, and pass the result through a function that decides, how strongly to activate. Beauty about it is, even though the idea is kind of simple when you think about it, when you connect thousands of thousands of neurons together, it's pretty crazy, just like our brains. Another question. Any guesses how many neurons are in your brains right now? Shout out a number.
3 trillion.
3 trillion? All right. Maybe not that high. Not that high.
Billion.
Way higher.
7 billion?
All right. It's about 86 billion. But in our case, we'll start off with like 10 in machine learning. All right. Let's break down the architecture of feed-forward neural network. It pretty much has 3 main parts: an input layer, hidden layers, and an output layer. The information moves forward only. It goes from input to output with no loops or feedbacks. That's why it's called feed-forward. Each layer takes what is given, performs a weighted transformation, applies an activation function, and then sends the result to the next layer. Another question for y'all. Why do you think we avoid loops in this kind of network?
Because there's a lot of
Say that again?
because there's a lot of
Yeah, pretty much. Loops create time discrepancies, which are handled by neural networks, and feed-forward neural networks is just simpler. They just focus on static data.
They create what discrepancies?
Time discrepancies. Do you want me to? Do you understand, or do you want me to talk more about it?
I kind of don't know.
Okay. Pretty much, loops create time discrepancies, meaning for feed-forward neural networks, you want to do what's most efficient time-wise. That's why I say time discrepancies. Yeah.
So, are you saying a feed-forward network, is it constant time?
Yeah. They just focus on the static data instead of recurrent neural network, for example. It's pretty much, if you want to take one thing out of it, it's simpler. That's what it is. All right, so we're getting into the math. So let's zoom into a single neuron right now. It's pretty much a building block of everything. Each neuron takes inputs like x of 1, x of 2, x of n, blah, 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 and it multiplies them by its weights, so w of 1, w of 2, w of n, and it adds bias, bias is b, and it passes through the result through an activation function, f. Mathematically, you have the formula right there, z equals w of 1, x of 1 plus w of 2, x of 2 plus, w of 3, x of 3, so on and so forth, plus b.
So is Z a neuron or is A a neuron?
Z.
What's A?
A is pretty much just A is just the function, just f of z. It's just an activation function. That's what it is.
Got it.
So I have another question for y'all. What do you think happens if we remove the activation function and just keep everything linear?
You end up with the linear regression in the end?
Yeah, exactly. You just get one big linear model, all the layers collapse, and the nonlinear activations, which is what makes deep learning deep. Okay. Activation functions. Activation functions are pretty much where the magic happens. They decide whether a neuron fires or not. In other words, how strongly each neuron signal moves forward. That's pretty much what an activation function is. We can go through some of the more important ones. Start off, sigmoid is a smooth S-shaped curve. The outputs are between 0 and 1, and it's usually great for probabilities. Tan H is similar to sigmoid, but it's centered around 0. So it helps when data has, if you have a data with positive and negative values, you'd want to use tan H. And ReLU, rectified linear unit, I have the function there. It's super simple, but it's extremely effective. ReLU became the default because it pretty much just avoids vanishing gradient problems that made deep networks pretty much impossible to train before. So after ReLU became a thing, pretty much everything else just collapsed, and this became the go-to norm of the industry. Again, without activation functions, every layer would just be linear combinations, and deep learning wouldn't exist. So activation functions are pretty important. Yeah.
Could you switch up Z to like not just be a linear combination stuff?
Did you say that again?
Is there any like time where Z is not like a linear combination stuff? Like is that like a different type of neural network or something? Or no, is that just like
No, I don't think so. No. Okay, I have another question just to make sure. Why do you guys think ReLU is important? And why is it so popular? You guys could, anyone answer? I don't know if I've went through it, but anyone has anything? Okay, okay. It's pretty much just because it's way cheaper. It's extremely cheap, extremely time efficient, money efficient, and it helps the gradients flow better during training. That's why everyone uses it now. Okay, forward propagation. Let's look at the forward pass now. That's the part where data actually moves through the network. The process is pretty simple. Input goes into the first layer, gets multiplied by the weights, summed up, activated, then passed forward. Each layer pretty much repeats the process until we get an output. The output is pretty much the model's best guess. At this point, the network hasn't actually learned anything yet. It's just making predictions based on the weights we gave. Does anyone know what's going to happen after we get that prediction? What do we do next once we get it? Anyone have an idea? Yeah.
Find the error.
Yeah, exactly. You calculate what was wrong, and then you find out what wrong using the loss functions. And speaking of loss functions, we're moving on to that. Loss function pretty much just quantifies how far off our model was from predicting like the actual true labels. In regression, we used mean squared error pretty much, which squares the difference between predicted and actual values. But in classification, we often use cross entropy, which pretty much just punishes the model in regular words, pretty much punishes the model more harshly when it's like confident it got something right, but it's actually wrong. It's pretty much like actual experimentation, but you're doing it online. The goal is pretty much simple. We're trying to minimize the loss. That's the entire goal of this. Every weight in the network will eventually just adjust to bring the loss down. Back propagation. This is pretty strong topic, but pretty much all this is after the loss is fully calculated, we need to know which weights were actually responsible for it. So back propagation uses a lot of crazy stuff, but pretty much just calculus, specifically chain rule. I don't know if you guys have taken calculus. It's pretty bad, but we pretty much use chain rule to compute how much each weight contributed to the error. That's pretty much it. And then we update the weight significantly or slightly in the opposite direction of the gradient using gradient descent, which is what last week's lecture was about. And pretty much the process just repeats itself for every single batch. So every epoch, that's what it is, until the loss pretty much plateaus and we kind of get a stagnant loss status. Who was here for last week's lecture? You guys should raise your hand. Okay, so a lot of y'all. Who remembers what a gradient tells us? Both of y'all. So you go first.
It was like the direction that points upwards in the function.
Yeah.
Yeah, I was gonna say the direction that points up would reflect the greatest rate of change.
Were they right? Okay. Okay. So speaking of that, we're connecting to last week's lecture now. Now that we've seen both forward propagation and backward propagation, we can tie everything back to last week. Last time we focused on gradient descent, pretty much how the model takes steps in the direction that minimizes the loss. This week, we've pretty much added back propagation into it. The mechanism that actually computes those gradients across the entire network is back propagation. That's why it's really important. So pretty much just think of it like this. Back propagation tells us like what to change, and gradient descent tells us like how much to change it. Together, they form like two halves of learning. Like you can calculate the blame, and then you make the corrections for it, pretty much. It's, yeah.
So is that the formula for back propagation? Or just
Yeah, yeah.
Okay.
Okay. To say it in even more like basic words, it's pretty much like you're teaching a kid how to shoot like a basketball. The missed distance from the hoop, loss, tells you how wrong you were, and the back prop tells you like which muscles to adjust to shoot better, pretty much. And the gradient descent would be like the tiny, like little physical corrections the kid would make for every shot. That was a good example. I have a few questions. It's like a pretty deep topic. Let's say if the learning rate is too high, what do you guys think would happen? Yeah.
Would you like adjust the parameters to drastically each time?
Yeah, just what would happen, let's say you ran it. What would happen if the learning rate was just too high? What do you think the output, like what do you think how the model would learn?
It would be inaccurate and jumping around too much probably with its predictions.
Yeah, yeah. You had something else to add?
I was gonna say like if they jump a little too far each time, then it wouldn't converge.
Yeah, exactly. And what if the learning rate was way too low? Yeah.
It would take too much time to actually learn.
Yeah, exactly. It would learn, but like you would have to wait there for like eternity to get like a simple thing done. So pretty much why I was asking those is finding the sweet spot is a part of hyperparameter tuning. Like you'll see in action when we get to start training these models. Hyperparameter is extremely important to not make sure like you're not over the learning rate or under it. All right, so an XOR problem. Okay, so let's bring this all to life with an example, like a famous example in neural networks, the XOR problem, so we call it. XOR stands for exclusive OR. The rule is pretty much simple. If the output is 1, the output is 1 if the inputs are different, and 0 if they're the same. So if your input's 0, 0, the output should be 0. But if your input's 0, 1, it should give you 1. And now if you plot this data on a graph, you'll pretty much you'll notice something. You can't draw a single straight line that separates the ones from the O's. That pretty much means a linear model is like logistic regression, for example, fails completely. You can't use a straight line to compute something like this. That's why a small neural network with just one hidden layer can solve it just fine, because it introduces nonlinearity. It can pretty much bend the decision boundary, which is why this became like neural networks became such a huge thing that this one discovery in like 1980s like pretty much reignited the entire neural network field and completely changed how we looked at it. You know, people realized that with enough nonlinear transitions or transformations, you could approximate pretty much any function you want. not just in lines, but in circles, spirals, anything. So I have another question for you guys. I know I haven't talked much about hidden layers, but what do you guys think the hidden layer's doing in this case? Any guesses?
What's the specific?
What do you guys think a hidden layer is just doing in like a neural network? Just what do you guys think like a hidden layer does? There's no specific examples. What do you guys think a hidden layer? Yeah.
It's calculating features from the inputs.
Yeah.
That might not be visible.
Yeah. Exactly. If you guys want to remember just one thing from this example, it's that linear models draw straight lines. Neural networks pretty much bend space and to make patterns linearly like separable again. Okay, choosing architecture. We can switch over to the practical side now, pretty much designing your neural network architecture. There's not really a single right structure to use. Choosing the number of layers and neurons per layer is just pretty much part of science, part of art. You can think of depth, how depth is just how many layers as your model's ability to capture like its hierarchy. Shallow models learn simple relationships, Deeper models capture like high-level concepts, pretty much self-explanatory. And width, how many neurons there are per layer, is what width is, pretty much just increases the model's capacity to store information. So for example, like shallow models, can you guys give me an example of like what a shallow model could be? What do you think a shallow model could learn of a simple relationship? Just give me like examples of simple relationship, like just anything, like 1 + 1 = 2. You give me one. You, yeah.
A simple relationship, 2 + 2 = 4?
No, I already gave an addition one. You have to give me something else. You gotta think.
Circle
2 times
versus
2 = 4?
All right, I'm skipping you. What did you say?
Circle or a square?
Yeah, that's pretty much simple enough relationship. And the deeper relationships are, let's say like, it doesn't even have to be actually deep. Let's just say cats and dogs. Like a model's trying to analyze cats and dogs. It doesn't know that a cat pixel is like, and the dog pixel are the same. That's a deep enough learning concept already. So it doesn't have to be actually deep. But pretty much here's a catch. More isn't always better. If, let's say, your model's too large for the data, it'll start memorizing instead of generalizing. And that's what we call overfitting. We do not want overfitting. That will just mess up the entire thing. It's very hard. But on the flip side, if your model's too small, it won't have enough capacity to learn data. That's underfitting. That's also another incredible pain. The key is to pretty much keep experimenting, start small, monitor your validation loss, and then just keep scaling up when needed. What do you guys think would happen when your training loss keeps going down, but then your validation loss goes up? Yeah.
I mean, it's overfitting.
Yes, exactly. So it's your model is memorizing the training data and not actually learning it. You do not want that again. Like one thing I can stress is you do not want overfitting in your models. We'll learn pretty much how to counter that with techniques like dropout, regularization, and like early stopping like later on. But again, overfitting is an extremely annoying thing to handle. All right. So some practical tips I can get y'all is here's some tried and true tips that will make your neural networks train smoother. First, standardize your inputs. If your features are all over the place, like one is in inches, like one of your things in inches, and another's $1, gradient descent will struggle. Scaling them, you have to scale them to similar ranges to help pretty much everything just converge faster. Second, use ReLU activations for the hidden layers, unless you have a good reason not to. They're fast, they're simple, they're reliable. And third, Initialize your weights properly. Techniques like, using like pronouns like he or Xavier to name like people. Initiations like make sure your activations don't just blow up or vanish as they like move through the layers. And fourth, monitor your validation loss. It's extremely important for during training. If it starts rising while training loss keeps falling, stop training. You're overfitting. And lastly, it's pretty much just shuffle your data whenever possible. Use a validation set or a cross-validation set to make sure your model's performance is consistent. Has anyone here trained a model? You can raise your hand. For the people that's raised your hand, have you guys ever trained a model that was perfect in training but like terrible in testing? Yeah, it's extremely common. That's a classic sign of overfitting. Your model is memorizing the data instead of actually learning the patterns. Neural networks are very powerful, but they're also extremely high maintenance. That's why you have to keep looking at these. Following these, best practices helps them pretty much stay stable and reliable, which is what you want. Okay, visualizing a neural network. Visualization is pretty underrated in my opinion, but it's extremely powerful. You can visualize activations, gradients, or even which features your network wants to focus on. In convolutional neural networks, for example, we can pretty much just see which parts of an image activates neurons. But in feed-forward neural networks, you can track the gradients, magnitudes, to pretty much just debug vanishing or exploding gradients. So why do you guys think visualization helps before deployment? Yeah.
You can identify like any potential errors.
Yeah, exactly. You can help catch bias, you can help catch dead neurons, or misbehaving layers, for example, before your model goes live, because you do not want that to happen after. All right, summary. Let's just recap what we've covered today. Feed-forward neural networks are the foundation of deep learning. The forward pass makes predictions, back propagation computes the gradients, and gradient descent updates the weights. Every deep model, CNNs, RNNs, transformers, everything builds on this exact pattern. Once you get this, everything else is just pretty much a variation of it. And that's pretty much like 90% of the battle. All right. We can go through a quick mini demo. This is pretty much just how all those concepts come together in code. Have any of you guys worked with PyTorch or anything like that before? Yeah. So this is pretty much what a very small code snippet would look like. These 5 lines pretty much just summarize everything we've learned today. Define, forward, loss, backward, update, all of them. First thing, obviously, you define the model. Then you'd this is forward pass. You'd compute the loss. This is for back propagation. And this is for updating weights. If you just get these, learn more about it on, other websites, this will be your best friend. If you just run this on like an MNI, ST, digits, or just a simple regression data, your model will actually start learning. I have another question. Which part do you guys think takes the most computing time? Yeah. Okay. Yeah.
I'm gonna guess back propagation. I'm guessing.
Get a more educated guess.
I was just gonna say because you have to calculate for the weights of each individual parameter. I guess I don't know.
Okay, your explanation was like pretty much right, but it's like just forward, backward. Okay, I was fully messing with you. it's back propagation. They're pretty much just forward and backward passes. They're full of matrix multiplications. It's like takes extremely long amount of time. And with that, we're done. Quick little. If you guys forgot to sign in again. That's pretty much it. Any other questions to end it off? Oh, what the hell?
Oh, no.
No questions? All right. Make sure to sign in if you guys haven't. But that should be it.
No, I'm just like. Yeah, I joined like a week ago, so I was like transforming.
The other guy I showed up.
Fully launched.
My first one was like 45. My second one was like
Yes, exactly. They're doing a competition now.
Oh, yeah. I was actually the judge for the competition.
Yeah, I should have
I'm like intermediate.
Okay.
What like grades are usually fun?
Like B3.
How does it
I mean on and off. I think like one week like probably like 2 weeks, but I have
They could also just tell you what
listened to
they Oh, yeah.
I've said it before.
That's cool.
Basically, the project
Like,
You do that. 16 is the orange one, right? Slamming the wall.
and then after
16 is the.
It's just like kind of like, you know,
and there's
it's like kind of like.
I know which way it's 13. It's on the side.
Yes.
Can you
But yeah, I didn't do that.
I couldn't do it. I could not do it. I tried so many times. Yeah. I couldn't
Start with like different problems, so like I'll be like.
I couldn't get to the left wall. Like the moment I put my hand on the left wall, I thought my two with the other hand on the left wall, and it was going to tip over, and then they would push themselves up. So then I put my left hand on the left wall, my hand on the left side.
I feel like they just had about 10 different genres. It was pretty easy. I just, it was like a.
so
And
completely.
I wrote a song for the shit. Yeah, and they did it.
Yes.
And I did my signature.
I thought you were gonna do Python.
Yeah, like 80%. It's very good. I was just saying that.
Yeah, it's alright. You always love good facts. Yeah, you do that makes it easier. Next time that's easier, probably. Those sides are right there. Next time for sure you'll have Yeah.
Some people tell you early birthday. In the group? No. It's pretty
That's how I learned. Do you get to think about flights? Do you think about hotels?
You didn't get anything. Some people do get, Rohan didn't get anything.
I mean, That's because Rohan came like a day late, and then he didn't like.
You didn't go to the Apple company dinner?
Yeah, it was,
The company dinners, they invite you on like.
Apple, I haven't heard of a single person about it.
The reason I was stressed so much
You gotta be in the, you gotta like tap it up.
I don't think Apple company did that. I've never heard of a single person.
I'm going to the Chevron lunch,
get out of the oven.
This Oakland dinner was pretty fun.
Should have taken me like 2 weeks.
Oakland dinner was actually like crazy too. All the food in there was on camera. It was like the last days of convention.
Oh, that's fire.
And they like rented out this place at Disney place, like having a restaurant.
That's cool. Like Disney Springs. What's it called? That's weird.
It was just like,
It's harder now. You gotta get that open. Kickstarter ordinance. It's like, you get a visa, so like, you know, like for the H-1B, it's not like all this. So when you make
Yeah, it's 100.
we got a win night, add it to our resume, print it out, and then go to the chef hacking on your chef with
Are the ticket prices?
It's the general price. Yeah, there's one on the actually for tickets, and you can transfer the seats.
Yeah, see, once they go like down,
yeah.
For sure, I know.
I'm trying to word this like in a way that was.
give them a take on this.
Making a paper on this?
I've been using chat for years, and it's like
Every time it's like just like something.
What's your major?
I'm doing copy and math, but I don't like, I don't like the copy classes.
I am,
This is like really. It's like basically like.
I might just do my math degree.
Image it, or G wasn't trained on it, you have 10 there.
Yeah, you get a C minor, right? Or CS.
Random image X.
Great, come here. So what is that? I gotta stop.
I was trying to optimize exercise. Like gradient.